Chapter 8 is going to deal with this idea of similarity. And I know that's a word you've seen before, you've actually used. We're not going to get too much into this concept of similarity right away. It's going to take a couple sections. We're going to do some introductory stuff. So for example, look at this section 8.1. It says we're dealing with ratio and proportion. And actually, today in class, we did some kind of algebra review. Okay, so we were just kind of refreshing. What do you remember back in pre-algebra? What's a ratio? How do you solve proportion? So you're going to see some of that today or right now, but we're going to take it a little bit further with our geometry concepts. Okay, a lot of similarity deals with ratios and proportions. So we got to master that before we can actually get to it. All right.
All right.
So what is a ratio? A ratio is the relationship between two quantities with the same units. Now, that's something we already talked about today, reminded you. Just hearing it again is always a good thing. And again, another way of thinking of that is this idea of a comparison between two numbers. Now, they do have to have the same units. So if I was saying I have 10 nickels and 5 dimes, nickels and dimes don't have the same value, so we'd have to kind of do some conversion. Sometimes we deal with feet and maybe meters. So make sure you're kind of doing that. Okay, so remembering that from earlier today.
And keep in mind, ratios are just fractions. If we want to write it as a fraction, we could write it as a fraction. Now, we're going to see some extended ratios that are going to look a little bit different that we can't really write as a fraction. But for the most part, a lot of times
most of the time we write it as a fraction. We can write it, we talked about it earlier today, the other ways, but fractions is the most common.
Okay, so we've got up here, it says the perimeter of a triangle is 56 inches, and the ratio of the measure of LM to the measure of MN is 5:4. Find the lengths of all the sides. Now, I want to clarify, when it says that we've got a ratio here, we actually have two ratios, LM to MN, and then we're comparing the 5:4. Do not forget that the order does matter. So the LM is referring to the 5 part of that, and the MN is referring to the 4 part of that.
So basically, LM is obviously bigger than MN.
Right.
Does that mean LM is 5 units and MN is 4 units?
That's a great question, but that definitely does not mean that.
Okay.
Okay. It's just saying that they're in the ratio. So if you think about a ratio, if I wrote it as a fraction, 5/4, I could scale that ratio up.
Yes.
All right. Or I could sometimes simplify that ratio as well.
But this is already simplified.
This is the simplified ratio.
Okay.
So we don't know what exactly those values are. We're going to find the lengths of all the sides. Now, I just want to draw your attention to the picture first.
Excellent.
What do you notice about that picture?
Well, obviously it's a triangle, and I see 2 congruent angles, which basically means the sides opposite are congruent. So LN and LM are congruent to each other. That base angle theorem converse.
Yes, exactly. You mean we're still going to use first semester stuff in second semester?
I think so. Looks like it.
So we know that these two segments are the same. They're congruent. This obviously is not marked as the same, and through the ratio, we're going to see that it's not either. Now, I like how you brought up the idea. Does that mean that if LM is listed with a 5, can I just call that segment 5? Well, let's think about that. If that had been 5, this would also be 5. This is the one that they tell us was 4. Does that give us our perimeter of 56 inches?
No, because perimeter would just add up those sides. That gives you a total of 14, which is obviously not 56.
Right. So we need to think about how to scale this up.
Okay.
Right? Or unsimplify our ratio, if that helps to think about it that way.
Okay.
Now, I just wanted to think about when you simplify a ratio, what do you usually do? Like if I gave you the ratio of 10/8, how would you simplify that ratio?
I would divide each of them by 2. And there's where you get the 5/4.
So what I want you to realize is you're dividing them by the same value.
Okay.
Okay? So to scale it up, we need to multiply it by the same value.
And we don't really know what we're multiplying. That's what we're trying to figure out, essentially.
So what if I just said x, some unknown value?
It's going to be the same number, so that's would make sense. You multiply by the same value.
So 5 times anything and 4 times that exact same value would still simplify to be 5/4.
That makes sense.
Okay, so when you are looking at basically scaling these up, because we're given a simplified ratio, we want to make it bigger to meet the criteria of a perimeter of 56, I could call this side length 5x, this one 5x, and this one 4x. They still meet that same 5/4 ratio, but now I'm not looking at necessarily the unsimplified ratios when I multiply those values each by x. And when I say perimeter, how would I find that knowing 5x's and 4x's?
Well, I would just add up those three sides. So add 5x plus 4x to get you 56. And that's going to be your 14x equals 56, which means x equals 4.
All right. Now, is that all I'm supposed to do is find x equals 4?
No, because it didn't even say find x. It says find the lengths of all sides. And what x essentially is what I'm going to multiply that simplified ratio of 5 to 4 by to get each length.
Right. It's our kind of our scale factor.
So if I was finding, let's say, LM.
Okay.
If I was finding LM, I would take 5 times 4, and that's going to get you LM of 20. So LM is going to equal 20.
And we know it's 20 inches, actually, since they gave us
Yeah.
the label. Okay. So then what about MN?
So I would take the 4 times the 4, and that gives you 16 inches. And then LN is going to be the same as LM, which we already knew that, so that's 20 inches as well.
Perfect.
Now, checking this, variety of ways I could think about it, they should add up to 56. And the other thing is LM to MN, is that actually simplify down to 5 to 4.
And that's good.
So 20 over 16 does simplify down to 5 to 4. Now, one thing I see with students on this one sometimes is that people want to just guess. They want to like just guess a number. This is not about guess and check. This is you communicating to us, how did you get it? So we want to see kind of this work on here. All
Definitely.
right? We want to see the support. And again, I want to stress Ms. Hooker said something great. Make sure you understand that this 5 to 4 is the simplified ratio. We're trying to find basically the unsimplified ratio, which is that 20 to 16 idea. Okay? All right, moving on. We have another example. This one says, we're dealing with a triangle, as you can see in the picture. It says the measure of the angles in triangle ABC are in the extended ratio of 3 to 4 to 8. Now, we have never actually talked about an extended ratio, so we'll talk about that in just a minute. The question said, find the measures of the angles. So we're just finding the 3 angle measures.
Okay.
Now, what exactly is an extended ratio? What do you think?
Well, it looks like it's a ratio, but it's just comparing 3 things instead of just 2 things.
And usually, by definition, a ratio is a comparison of 2 things. So when you have an extended ratio, sometimes your approach to it could be a little bit different.
Okay.
So keep that in mind. Sometimes when you use an extended ratio, you may not use the whole thing. Sometimes you will, okay, just depending on the scenario. You're still comparing some stuff. Now, like the last one, if I just say, okay, well, and they don't tell you which angle is which, right? So if I say this is the 3, the 4, the 8, would those actually be the degree amount of those angles?
No.
No, because if I add 3
That's
plus 4
definitely not
plus
180.
8, that's not 180 degrees. Okay, so kind of like the last one, 3 to 4 to 8 is basically, this is your simplified ratio. This is
Okay.
already simplified.
So
Right.
can I just put the x's with it again?
Yeah, because what we want to do is, like Ms. Hooker said in the last one, scale it kind of up. So if I multiply each of them by x, because we don't know what we're multiplying to scale it up, that will allow us to set up an equation to find that value, to find the angles. So what's true about these angles again?
We know that they add to equal 180.
So I'm going to go ahead and add them up, set them equal to 180. And when I go ahead and solve it, I get 15x equals 180.
So x is 12.
And again, we're not done.
Right,
So-
that's just x.
And guys, here's the deal. It didn't tell you which angle was which. So if you put angle A as the 4 and then this was the 3, doesn't matter.
So, okay, and I guess I've always told my students in the past, too, that because they said A, B, C, it should be in that order. Is that not necessarily accurate?
Not necessarily. Yeah.
Good
I
to
think because sometimes they won't even give you a picture.
Well, and that's true. Usually
They
wouldn't-
usually don't even give you a
That's
picture.
true.
This ratio, if they don't specifically say the ratio of angle M, angle A to angle B to angle C, they're not really
Okay.
specified. I can't even talk.
specific.
Yes, they're not specific with that. Then
Yeah.
it can be anything.
Right, okay.
All right.
Good
Now, let's go ahead and find each angle.
Okay, so then the measure of angle A from what we have, so the 3x, 3 times 12, is going to give us 36. Measure of angle B was our 4 times 12, so that's going to give us our 48. And the measure of angle C will be our 8 times 12, which is going to give us a 96.
And to check this, what should be true about the 3?
They should all add to equal 180.
And if I simplify down 36 to 48 to 96, it should simplify out.
And if you divide them all by 12, it's going to get you right back to your 3 to 4 to 8.
Exactly. So these two are very similar problems. Just it's kind of taking that idea of a ratio and applying it to our geometry.
All right. Some vocab. When we talk about a proportion, because we're going to be dealing with a lot of proportions this chapter, a proportion is just an equation that equates two ratios. It says that two ratios are equal. You're going to see these words means and extremes, and just realize that when we talk about means and extremes, they're catty-corner from each other. That's the important part, because since this is an equation, it does not matter which order you do them in. It doesn't mean that I have to always do the bottom of the first one and the top of the second one. The things that are catty-corner. One will be your means, one will be your extremes.
Good. Okay. And we kind of already talked about proportion today, so you guys have this background,
it's
but
just
this is stressing it again. We
are going to dive more in depth with the idea. Well, you're going to see the words means and extremes just in some of our vocabulary, so in some of our theorems. So.
And yeah, that's the whole point of these words, as you'll see on this next slide. Most of you will recognize this first property that you're going to see. There are a total of 4 properties involving proportion. We are discussing only 2 right now. You'll see the other 2 tomorrow night. Okay, so we're kind of dividing it up. The first property, I'm hoping this is the one you've seen before, called the cross product property or cross multiply. A lot of times people say this. This, to me, this property right here is essentially helping you solve a proportion. Right. This is how you get to a good point in a proportion to actually do all the other stuff that we normally do. So what exactly is the cross multiplication or cross product? Is the product, which means multiply, the extremes, here's where that vocab, to equal the product of the means. Okay? So it's basically telling you're multiplying certain things. So if I was multiplying the extremes, now, really, does it matter again?
The order.
No. So if I have this proportion, I would multiply
AD.
And that's going to equal
BC. Which is what we do when we cross multiply.
Exactly.
It's just multiplying those pieces that are catty-corner.
It's just some different lingo, basically.
And it's also just realizing this is a property of proportions.
Now, the second property, I want you to take a look at the actual property, the if-then statement here. It says, if two ratios are equal, then their reciprocals are also equal. That's why it's called the reciprocal property. So basically, what am I going to have to give you to begin with? Well, I'm going to have to give you a proportion because these are two ratios that are equal. They say that the reciprocals are also going to equal.
So that's saying like B over A should also equal D over C.
And basically, you're just doing the reciprocal of this. Now, why would this actually still work?
Well, as I look at this one, I'm kind of thinking back to that cross product property for a minute, and I'm still going to get that AD would equal BC when I cross multiply.
Yeah, it's still going to get the same outcome. So this is just another way of writing the equation.
Okay.
Now, if I found the reciprocal of just one of them,
that wouldn't work.
It wouldn't. It says reciprocals, they're reciprocal, so that means both of them. Okay. To me, reciprocal property, it's not necessarily helping you necessarily solve. It just allows you to be able to see that maybe one person could set it up differently than the other.
Okay.
And there's nothing wrong with it. It's just allowing you to set it up differently.
Okay.
So,
all right, we are going to take a look at another example. It says the ratio of the side lengths of triangle QRS to the corresponding side lengths of triangle VTU are 3:2. So that means that for every side length that I have over in this first triangle, that would be what? What part of the ratio, I should say?
The 3. Because it's saying this to that, in a sense.
And everything in this triangle would be representing the
2.
Now, obviously, these are not all side lengths of 3, and these are not all side lengths of 2. That's the ratio.
Okay.
Okay. They want us to find the unknown lengths.
All right.
So that's telling us that these two triangles are really similar. Okay, because they have a ratio that represents those corresponding sides.
Okay.
Okay, so we have a ratio that they've given us of 3:2. We need to compare some side lengths in one triangle to help us to find some side lengths of another triangle.
Okay.
Okay? So what sides do you see that might be corresponding sides from the order that they've given us, that they've written?
So based on the order of the name, QR corresponds to VT. And I look at that and that they don't have any.
I shouldn't put. I don't
Yeah,
know how
they're
to
not
mark
necessarily
it.
congruent.
They're not congruent, but I don't know how to mark them. But
You could write off the side QR over VT.
There we go.
Why don't you do that?
Over VT. Those two are in a proportion or in a ratio with each other. Okay.
And another would be like RS over TU. And then the last one would be QS and VU.
Great. So all of these are that 3-to-2 ratio.
Yes.
So now we just need to figure out what pieces do we already know that can help us to find some other pieces.
Okay, well, I'm looking at the first triangle, the one on the left. SR is 18, so I'm looking at, there's RS, so that would be 18.
Okay, so I could replace this with an 18, and that would allow me to find TU.
Yeah, it's a proportion. There's
a
one
proportion.
unknown. We could go ahead and do that cross multiplication.
Okay.
So that would be 3TU equals 36. So TU equals 12. Now, I'm going to comment on the fact that she kept TU in the proportion. She didn't just put X, right? And often people will do that, and there's nothing wrong with it, but the problem with you keep using the same variable, you're saying they're all the same, one. The other thing is, how do you know what X is representing?
Right.
So if you use the actual name of it, that helps to me.
Yes.
If you choose to use a variable labeled, mark it in the picture. Okay.
And then give them each different one. So maybe call that one Y or call that one, call just something different so that way you know. Okay, great. So we've got one of those unknown lengths.
Okay.
Okay, and I'm even going to mark it over here just so we can keep track.
Perfect.
Which ones we already know. 12 centimeters. Okay, what else do we know?
I know UV is 2 centimeters, so I'm going to go to that one right there. Say that's 2. And, well, I could cross multiply, right? But I see the denominators are exactly the same, so that means QS is just 3.
Definitely.
Hopefully everybody sees that too. So 3 centimeters as well.
Yeah. Okay. Now, they ask us to find the unknown lengths. I also don't know these lengths here. Is there a way to find them? Because I don't know either one of them, so I can't set up a proportion right now.
Yeah, because there's 2 unknowns in that proportion.
Right.
You can't have 2 unknowns in one equation unless you have another equation. Well, I am noticing that these are both right triangles.
Oh, that probably has something to do with it.
And the fact that you have 2 sides in a right triangle, you could find their third side by using the Pythagorean theorem.
All right. So which triangle do you want to start with?
Let's start with the one on the right.
Okay. So we would say that
12 squared plus 2 squared equals the TV squared. So 144 plus 4. So that's 148.
So then TV.
And TV is equal to about 36.5 centimeters. Now, we've talked about when do we round, things like that. This is one for sure I would round because of the fact that you're dealing with units of centimeters. You're not going to say, well, the answer is the square root of 148 centimeters.
Right.
Okay.
When you're actually measuring, you do, and especially centimeters, you do use the decimals too. So that's good. Okay, now, would I want to set up a proportion with the 36.5 to find this other length?
You could. Well, here's the deal. You would have to use the TV's answer to do that, and TV's answer is a rounded answer, and I don't want to use a rounded answer to find either.
Now, you could use the radical 148. That's going to get kind of ugly, but you could do that. Or you could go ahead and just use the Pythagorean theorem again.
So I would just do that. And the other reason why I wouldn't use the TV to find QR is because what if you make a mistake on TV?
Absolutely.
Then you're going to make a mistake on the QR. So this ends up being, so that'd be 9 plus 324. And that gets you 333 equals QR squared. So QR is about 18.3.
Oh, 18.3, yes. Centimeters. All right.
And we have all 3. Now, all 4 actually, sorry, all 4 segments that we had to find. Something to keep in mind is you could check to make sure, did we do the calculation
something's not right? Because radical 148 should not be more than radical 333.
Maybe I looked at the wrong one.
Radical 333 is the 18.24, but radical 148 is 12.16. So I'm not sure what I was doing there when we did it earlier. 12.16. Sorry, guys.
Most of you are probably like, they're wrong. They're wrong.
Wait, what did I say?
So 12.16.
So about 12.7.
16, so it would be 12.2.
Oh, was it one? Now I'm looking at it upside down, so that doesn't help either. 12.2. Okay.
See, this is what happens when you make.
Look at that reasoning that I had right there, Mrs. Flimmer. I thought to myself, that can't be right. That this is more.
Why couldn't
because that was in the 2 ratio, not the 3.
I love that you did that.
And then I thought, well, then let's look at that. Radical 148 is definitely not more than radical 333.
No.
So
and I was about to say, we could check this. Take each segment, so like QS, and compare it to UV.
Yeah.
That's a 3-2. SR to TU. That's also 3-2.
And you can check the 18.3.
18.32 or 3 to 12.2. Now the problem with
they may not be exact.
Yeah. And so when I do that, let me just type that in real quick. You end up getting, it ends up being 3/2.
Okay.
Just because we rounded correctly.
Yeah. All right.
Last one. It says we have a photo of a building that has the measurements given in the sketch below. This is a photo. So obviously it's not exact. This is kind of a scale in a sense of it. The actual building has this amount of width, so 26¼ foot wide. The question is how tall is it? Now, to me, one thing to keep in mind is you're talking about, in a sense, a proportion, because you're talking about comparing a smaller scale to a scale of the picture to the actual one,
right?
Okay,
and you guys have done this with shadows and trees.
This
and
is not
stuff
a new
before.
concept.
This is
Now, one thing that I often see mistakes on is this idea of, it says it's wide, so many feet wide. How do I know what that actually corresponds to in the actual the photo, not the actual building, the photo?
Yeah, we know that one thing that we want you guys to realize is the length is always going to be the longer of the two. The width will always be the shorter.
So out of these two, this would be
that would be my width.
Okay, so kind of keep that in mind. If it helps to kind of draw a little quick sketch, obviously the actual building's going to be taller than this. So this would be 26¼ feet. And then we don't know how tall it is, so this could be our X, our unknown.
Right.
Okay?
Yes.
So what other things are you thinking on
Well, okay, I'm thinking a couple things. I'm thinking, first of all, we have different dimensions, which, depending on how you set up your proportion, may affect that.
Okay.
Okay, I know that a ratio has to have the same units. So if it was me and my ratio, I would want to say the 1 7/8 compared to the 2.75, I would want to make a ratio of those two, because they already have the same units.
Okay.
So I'm really comparing a width to a length, and it should be equal to another width to a length.
Now, technically, though, you could do width to width without converting, because in a proportion, you don't have to worry about the units.
Right.
Okay?
Well, you do, but in you have to make sure that the things that are within one figure are the same units.
Yes.
Yes. So I hope we didn't confuse you guys on that.
No.
But anyways, so you could do it either way.
Yes.
But I just want you guys, when you're thinking of a ratio, when you're first setting that up, if you think, oh, I want to keep those the same units, that's okay to do too. Typically when we talk about similarity, we're going to be looking at comparing those pieces that correspond. So we're going to be writing our ratios with the 1 7/8 would compare to which piece in the other figure.
Yeah.
So let's go ahead and do it that way, but I just wanted to talk.
I
wanted to have the discussion about the fact that it's okay to do really either one.
You can do width to length. The key is kind of what she's saying here, is you just want to make sure you're consistent. Whatever you're doing, you got to be careful with both of them. Right? Now, the other thing I'm noticing is there's some units dealing with fractions and decimals. If the fraction converts to a decimal nicely, which I think 7/8 does, I would go ahead and put it as 1.875. 875, and then this is obviously 26.25. That to me would be a little easier to work with. Now, if it doesn't, we don't want to round to get another rounded answer. Okay?
Right.
So if we're going to go with that width to length idea, keep that kind of consistent. So it'd be 1.875 over 2.75. And we don't need the units actually in the problem. Equals 26, sorry. I see the 0.25. So we're doing width to length, or height, because it's talking about how tall it is.
Yeah.
And we don't know how tall the other building is.
Right.
Now, one thing to keep in mind, when you do get your answer, you're talking about how tall the building is. So since I have no units in this, okay, don't get confused. Are we dealing with inches of the building?
We're
or
dealing with feet.
We're dealing with feet. So keep that in mind. So we do a little cross multiplication, all right?
Okay. So you get your...
And then over here you get what? 72.
0.1875.
And when you go ahead and divide, you get 38.5.
Yep.
This is feet. Now, another way you could write that is 38 feet and how many
Now, I have a lot of kids that don't want to say
inches?
5 inches. It's
Okay.
not 5 inches. It's a half of a foot, so it's 6 inches.
Good.
So be careful with that conversion if you do convert the decimal back into...
Good. And
The
guys,
fraction.
think logically here. It's obviously going to be taller than the actual photo. And it's also the fact that you're talking about how tall it is, it's going to be taller than the width. So you should expect something larger than the 26 and a fourth feet.